Questions? As in, are there any? Besides the one I just asked. So for the last problem of the test, that's a week from today, you'll have a problem similar to what you just did. Do you want the answers to be integers?
That would be nice.
Okay. The downside is if you solve it and don't get an integer, then you know you've done something wrong. But, yep, we'll make them integers. There it is. We last left off. We had just done the RC AC circuit. So let's sort of drop back just a little bit. And I know that I create an EMF by having a changing magnetic field, or a changing magnetic flux, more specifically. Oops, that's right. This is calculus based. And this induced voltage will create a backcurrent that will try to mitigate the changing magnetic flux. It'll either try, if the magnetic flux is getting bigger, it'll try to make it smaller. If magnetic flux is getting smaller, it'll try to keep it bolstered up. Well, if I have a solenoid, I know the magnetic field, or the strength of the magnetic field going through the solenoid is going to be mu naught times the coil density times the current. I believe we did derive that. Well, if it was over there, it's been erased since. We did derive this? Okay. So if I have a solenoid here, and my current changes, so if delta I is not zero, in other words, I have a solenoid in a circuit and I just turn it on, then I will have a change in my magnetic field, therefore I will have a change in my magnetic flux that is happening in the middle here, because this is the magnetic field that's inside the solenoid, assuming an ideal solenoid. So the EMF that I am producing will be the negative ddt of B times A, and I'm just going to ignore the negative sign for now. Actually, no, I am going to keep it in. So this would be the voltage that is created by this changing magnetic field. Since my area of the solenoid is staying constant, that's the area of the coil itself. That area pops out, and I'm left with dB dt. The area of my coil is, well, I've got a coil here, so the radius would be pi r squared. But I also have a whole bunch of coils. So if I have n coils, capital N coils, then my area really is n times pi r squared, because each one has its own area. Lost room for the negative sign, negative times dB dt, and the magnetic field is mu naught little n, the coil density, times the current. Well, mu naught is constant, that's the permeability of free space. Little n is the coil density, it's the coil per unit length. So, n coils, the length L. So that's a constant for a particular geometry. And so I have negative n pi r squared U naught little n di dt. This is dependent upon the configuration of the solenoid. Pi and U naught constants, but n, r, and little n are all related to that. And matter of fact, since little n is equal to the number of coils per unit length, I can make that substitution here, and I get negative pi r squared n squared pi r squared n squared U naught over L. Of course, I did make the assumption that these are round when I put in the area of pi r squared. I could, if it's not round, then it's the area of whatever the shape is, times di dt. These are not. So this would be the potential difference as you're going across this set of coils. There's no resistance in this set of coils. This is a nice ideal inductor. This is called an inductor. And an inductor has an inductance, which is generally symbolized by a capital L. And that's the formula right there. Or slightly more generally, whatever the area of one of the coils is, n squared U naught over the length. And presumably, some of you discovered this over the past week as you were doing the induced current lab, induced voltage lab, whatever, induced whatever. Electromagnetic induction. I think that's what I called it.
So it can't be considered as a capacitor? The solenoid?
No, it is not a capacitor.
Or a conductor, I mean. A conductor.
Oh, well, it has to be a conductor because current has to go through it. But if you have the wire that's wrapped up like that, it also serves as an inductor. Actually, I'm going to go grab the prop. Be right back. I'm just going to let it roll. All right, so we were using a solenoid, or just acknowledging the solenoid has an inductance. Now, in a circuit, the big difference between something that's called an inductor and something that's just a solenoid is the size of the wires. That if you'll notice that this one has fairly thick wires associated with it, which means the resistance is much less. Unlike this right here, in which they're very thin wires, it's going to have much greater resistance. So in terms of the mechanics of it, this is what would be considered an inductor, and this would be more of it's actually a toroid, but a more solenoid type. However, solenoids do have an inductance. So let's just play around with this idea for just a moment. So we now have that the voltage of an inductor is negative L di dt. So that's why in the lab you were figuring out at what rate did the current change so that you could predict what this back EMF is. So let's say that I have a capacitor that is fully charged in a circuit with an inductor. And if you need something more, how realistic is that? Well, there's no resistance, so there's some lack of realism there, but I have let's say I have an open switch, and I close the switch. So I have a charged capacitor, I close the switch, there's an inductor in there. Just for the sake of ease, I'm gonna assign a positive and negative side. So I know that the change in the voltage across the capacitor plus the change in the voltage across the inductor has got to be 0. As I go around the circuit, this is the charge divided by, actually I'm going to do an intermediate step first. So this is the change in the voltage of the capacitor minus L di dt is equal to 0. Voltage is Q divided by the capacitance. Now, I do need to put an extra subscript in here just to clarify. This is the charge that is on the capacitor. This is the current that's flowing across the inductor. If I did dq CDT, that would be the current that is flowing off of the capacitor. So we do it a little bit differently here. So recognize that the charge that is on the capacitor is charge that is not flowing across the inductor. At any moment, this Q sub C and this current are they're related to each other, but that is not complete. That I start out with whatever my initial amount of charge is on the capacitor, and that's going to be equal to the charge still on the capacitor plus the charge that's flowing across the inductor, or that has gone across the inductor. If I take the time derivative of this, dq CDT, 0 equals dq dc plus dq L dt. This is the current flowing across the inductor. And that is equal to the negative dq CDT. Because ultimately, when I'm going to need to solve an equation here, it'd be nice to, if I have one equation, to have one variable. So I can now express this equation here in terms of just QC. So I have the charge that's on the capacitor divided by the capacitance minus L times negative ddt. Actually, L times ddt of negative dqc dt equals 0. So I have a second order differential equation. Fortunately, there's no single integral in there, so it's relatively simple to solve. All right, questions up to here? So I have Q C over C plus L second derivative of Q equals 0. So I need some function here. If I'm going to describe QC, I need some function that the second derivative is basically the negative of what we started with. And what function has a second derivative, which is basically a negative of what we start with? Say it again?
Sine.
That works. So if I let QC equal some amplitude times the you said sine, not cosine, times the sine of omega t, then the first derivative with respect to time is a omega cosine omega t, and the second derivative with respect to time is a omega squared, negative a omega squared sine omega t. So if we stick that up in there, we have a over c sine of omega t plus negative L A omega squared sine omega t equals 0. And this is true as long as, well, we get rid of the sines and get rid of the a's, so it's true as long as 1 over c minus L omega is equal to 0. And so we can solve for omega, and that's the square root of 1 over LC. So therefore, if my charge therefore my charge can be modeled by this function of time, which is my amplitude times the sine of the square root of 1 over LC sine omega t. Except the trouble with sine by itself is when time is equal to 0, what is the sign?
Zero.
Yeah. Which means that the charge, if sine is sufficient, the charge here would be 0 to start with. And we know that's not the case. The premise was that the capacitor is fully charged. So QC can't be 0, it has to be that amplitude. So so if I'm using sine, I need to throw a phase shift in there, plus 5, plus 5, plus 5. Pretend. Oops. I know when time is equal to 0. Wow, that is just really bizarre notation there. Let's try that one again. There we go. I know when time is equal to 0, I need to have the amplitude equal to, or QC needs to be equal to whatever that maximum charge is. Whatever, just for the sake of this, just call this Q sub naught. And if QC equals Q sub naught, if time is equal to 0, then phi has to be pi over 2. Because that term drops out, the sine of phi has to be equal to 1. And so we now have a function which can describe it. So therefore, we end up with QC equals whatever that maximum initial charge is times the sine of the square root of 1 over LC times time plus pi over 2. Just to make it pop. Ooh. Realize what this is saying to us. No resistance, and that is key here. I have no resistance. I have this fully charged capacitor hooked to an inductor. And so what's going to happen is all the charge is going to go from the positive plate through the inductor to the negative plate, and then it's going to go back again. And this thing would oscillate on forever in our nice ideal Bohr problem. If I did not have the inductor in there, the charge would just immediately zip over to the negative side, neutralizing it, and you'd have an empty capacitor. Questions?
So because of that phase shift, could you do cosine.
Yeah, which is what I tend to do with this one. Sine works, as long as you bring in the phase.
Do one other DC circuit before we get over to the AC. And again, questions while I'm erasing? Hopefully nothing to do with what I just erased. RL circuit. Yeah, I'm pretty sure that's all I stuck in there, yeah. So I know that the potential gains and losses must add up to 0 when I go into circuit. So if I just start here and work my way around, the change in R, try that one again. Change in the voltage, change in potential across the resistor plus change in potential across the inductor must add up to 0. Make sure I got the,
Yeah.
so this would be negative IR minus L dIdt is equal to 0. And now ultimately we're going to just solve for I. I have a first order differential equation. So whatever you do to solve it, but I'm basically going to get them on the other sides, then get all the i's together. So I have negative IR equals L dIdt. I have negative R over L dt is equal to di over I. And then I integrate. So negative R over L time plus a constant. Let's use K for the constant is equal to the natural log of I. And so my current is equal to